The James Webb Telescope is a scientific marvel, one that's cost $10 billion but has sent us back priceless views of the cosmos never seen before by humanity. We've seen the images that it has provided, but we've never really understood how it achieves the accuracy, clarity, and beauty that it does. The James Webb Telescope is already peering into the universe's past life, identifying galaxies that are over 12 billion years old, which were created just after the Big Bang. But many of these first images weren't really pretty at first. They took a lot of time, modification, analysis, and cosmetic treatment before they reached our eyes. So, what's the process behind it? And how does it achieve those glorious views? Here's a quick refresher of the stuff we already know about the James Webb Space Telescope. It is the largest, most effective, and powerful space telescope ever made. On December 25, 2021, NASA's scientific marvel, built with unmatched infrared detection instruments, launched from the European Space Agency's launch site in French Guiana, aboard an Ariane Ariane 5 rocket. On July 12, 2022, NASA released the first scientific images from Webb, and if you haven't seen them already, you really ought to. The $10 billion James Webb Space Telescope will be used to investigate the history of the universe from the Big Bang to exoplanet formation and beyond. The Webb is one of NASA's great observatories along the likes of the Hubble Space Telescope. These huge space instruments look deep into the cosmos. The James Webb Space Telescope took 30 days to travel nearly 1 million miles or 1.5 million kilometers to its permanent home called the Lagrange Point 2, or L2, which is a gravitationally stable location in space. The telescope arrived at L2, the second Sun-Earth Lagrange point, on January 24, 2022. L2 is a point in space which is near Earth and that lies opposite the Sun. This orbit keeps the telescope aligned with Earth as it circles the Sun. Other space telescopes like the Herschel Space Telescope and the Planck Space Observatory have also been used there. According to NASA, the James Webb Space Telescope will study 4 main things: the first light in the universe, how galaxies came together in the early universe, how stars were born, and how planets formed, which includes the origins of life. NASA released the first science images from the James Webb Space Telescopes during a live event on July 12, 2022. They showcased the cosmic cliffs in the Carina Nebula, the spectacular Southern Ring Nebula, Stephan's Quintet, and the atmospheric arrangement of the hot gas giant exoplanet WASP-96b. The first ever science-quality image captured by the James Webb Space Telescope was unveiled by President Joe Biden, Vice President Kamala Harris, and NASA Administrator Bill Nelson a day earlier on July 11, 2022. The image was created using just 12.5 hours of observing time on one of the telescope's 4 instruments, according to a NASA statement. The image was NASA's first deep-field image of galaxy cluster SMACS 0723. Which showed thousands of galaxies, including the faintest objects ever seen in infrared for the first time. All right, since we got the basics out of the way, let's move on. Eric Roslowski, an associate professor of physics at the University of Alberta, was among the first Canadian researchers to put the world's latest and greatest space telescope to use. In his case, by observing star formation in the Triangulum galaxy, also known as Messier 33. Roslowski excitedly revealed, "When my project was executing, I was pulling data out of the archive as soon as it was landing. I sent a picture of it to my uncle. Hey, Uncle Mike, you and I are the first people on Earth to see these pictures." A sweet gesture for sure. His Uncle Mike, a backyard astronomer, is the person who first got Roslowski interested in astronomy. From there, he went on to get images of a galaxy 2 million light-years away from a $10 billion telescope in orbit around the Sun, 1.5 million kilometers away from Earth. The picture Roslowski sent to Uncle Mike was important for them both, but it was a lot less sensational than the picturesque full-color pictures NASA released of the JWST as it amassed attention for its high-resolution infrared views of the universe. Instead, the picture sent to Uncle Mike had a few light blobs on a dark background with banding across it. The Hubble image of Triangulum, or even Roslowski's partially processed Webb image, both of which show millions of stars, the spiral arms of the galaxy, and some turbulent areas where stars are born, is very different from the Webb image that we've come to see, which shows only a few stars. The difference between the images shows how researchers translate raw data from the JWST into images that can be used for research and which the public has marveled at. To be honest, Roslowski's initial data, which is part of an actual astronomical image, appears in his computer code that doesn't necessarily look pretty unless you're into that sort of thing. What he sent to his uncle was, according to him, a quick and dirty look at the Triangulum galaxy. Before those images or data can be useful to him as a researcher, they have to be fixed, especially because the equipment has its own quirks. Even though the JWST was carefully designed and built, the raw data it produces is uneven. Images have to be straightened out for imperfections intrinsic in the cameras themselves. Cosmic rays can create static in the camera's detectors, so the telescopes capture multiple versions of the same image to fix this problem. Even the pixels, the smallest unit of the telescope's detectors that are sensitive to light, are different from each other. For example, one of the more than 1 million pixels in the JWST's mid-infrared instrument, or MIRI, might be more sensitive than its neighbor, while another might be less sensitive than its neighbor. The JWST engineers have a solution for this, a complete calibration map that shows how to adjust each pixel in each instrument on the Webb telescope to compensate for the variations. Roslowski says this is the work of hundreds of people. When we say commissioning a telescope, it launched, and then they went through this period where you heard nothing about the results. That's what they were doing up there. It's finally turned on. They're starting to make images and say, how do we take out all these corrections? He says that all he had to do is use the JWST's map of pixel calibrations to adjust his data to account for those variations in pixel sensitivity. For most researchers, much of this technical work takes place in what they universally call the pipeline. It's kind of like a data processing highway where the raw data received from the JWST is changed as it travels from source to destination. Along that highway, some software might correct the data based on inconsistencies or abnormalities in the detectors. Other software might correct the data based on calibrations for the cameras, and might combine the data from multiple exposures into single images. There are also a number of off-ramps on the highway from which researchers can extract their information at earlier stages of the processing. In Roslowski's case, he wanted some of that raw data rather than the end result. It's nice to have something to send to a loved one, but researchers don't do science based on pretty pictures, says Roslowski. He often works with the raw data alone. Roslowski says, the pretty pictures are wonderful for interpreting and building up and telling a story. But then backing up that story is what requires doing the computer processing to figure out how to measure every star in this image. Figure out what it is, and then use that to back up your claim. Most of my job is programming, so I'm writing the computer code that is going to take this big chunk of numbers and turn this into properties of stars. That is my day job when you get down to it. For Alyssa Pagan, though, things are very different. She is a science visuals developer for NASA. She's one of the people who worked on processing the amazing Webb Telescope pictures that were released to the public. The image of the Carina Nebula, one of the first 5 images released from the JWST, was the first she had worked on from the Webb. She commented on the experience, saying, "It was insane. It was gorgeous, honestly, to me from the get-go. The fact that you are one of the first people to see the image and process it and put it out for the public, it was a huge honor. And it was also a time to reflect on how far we've come and all the people involved to make it possible." For Pagan, the images she started to work with were at the end of the pipeline, where most of the rectifications and artifact removal had already been done. The Carina Nebula image was made up of 6 different images of the nebula in different shades of infrared. Each image was taken with a different filter and showed the nebula differently, and the Webb telescope sees in infrared, so the images that Pagan was modifying were quite different from the ones we see now. The raw images she started to work on weren't quite picturesque just yet, with some white dots on a dark background and no detail at all. That's because the JWST camera's dynamic range was too wide for even Pagan's high-end computer monitors to show. Her monitors weren't able to see the information in the dark parts of the image. The solution was to make the blacks and whites closer or compressing it together so that it would fit in the range of her monitor. Weirdly enough, this is referred to as stretching the image. After it was stretched, she was able to see detail in the images, such as the fainter stars and the cloud of dust and gas that make up a nebula. But she still had to choose colors for each of the black and white pictures, and this isn't done randomly. What we call visible light is only a small part of the electromagnetic spectrum. This is the part that our eyes can see. At the end of that section, where light has shorter wavelengths, our brain thinks of those colors with a bluish tinge. At the other end of the section, where the wavelengths are longer, it assigns reddish colors. On either side of the spectrum that our eyes can see are wavelengths that our eyes can't see, but which other animals or special instruments can. The wavelength of the spectrum that the Webb operates in is beyond what we can see with our naked eyes, but we can see with our long-term vision. In astronomy, its advantage is that infrared light can pierce clouds of dust and gas that block visible light. It means that we have to create a representation of each image that the Webb has captured in order to see what it saw. And to add color to those images, Pagan uses the same rules that our brain does. Short wavelengths are blue and long ones are red. After she finished that, she could put those colored pictures on top of each other to make one big color image. She says she began to balance science and beauty at this point, commenting, "That's when it becomes quite subjective. We are working with scientists through this process to make sure we're showcasing the data as much as possible, and we're being as honest as possible. But it is subjective now because we are adjusting like tonality and contrast, color, and all these things to really make the features in each filter more prominent, or just to showcase and highlight those different regions." Pagan used Photoshop to modify the image to produce something both aesthetically pleasing and scientifically accurate. I guess even NASA photoshops their images. When NASA released the Carina Nebula image on July 12th, it amazed both astronomy fans and scientists. Many people had been waiting for years to see the depths of the universe through the eyes of the most powerful telescope ever made. Canada's JWST scientific director René Doyon described it quite well, saying, "The beautiful bridge between science and art." Pagan also adds to that, saying, "It's so cool to see everyone talking about it. It feels like a nice, connected, universal moment of appreciation for science and humanity." So, what images do you think the Webb will capture next? And what would these images really look like if our human eyes had a wider color spectrum? Let us know in the comments below. And as always, thanks for watching Space Rumor.